Okay, good morning all again. Today we are going to run a new subject, which is the torsion. I'm going to explain what the torsion is and how it affects our sections. Then we're going to make a stress torsion effect. Here, let's get started. Okay, the subject is torsion. Torsion is in Turkish burulma. Burulma. Okay. If you take a look at Turkish book, you can see the subject under burulma title. Okay. Here, let me explain what the torsion is first. Let's draw a section, a circular section here. A circular section. This. And the axis of the section is here. If we apply a moment which rotates this section around its axis, for example, like this. Okay, this is MB or MT, whatever. This is the torsional moment. What we are doing, you can see my pen. It's a circular section. What I am doing, we apply a moment around its axis. Okay, I try to make a torsion on the section. This moment is torsional moment. Actually, instead of B, let's write T. That's better, which represents the torsion. MT. Okay, torsional moment. This is better. In this subject today, we are gonna talk about. By the way, you know what the torsional moment and torsional effect is. If we rotate the section around its axis system, so we will get torsion. So torsion, there are some important things. In torsion, the stress and strain, gerilme ve şekil değiştirmeler, depend on the cross section shape of the structural member. Okay, the important thing here is our stress and strain depends on the cross-section shape. So you may have a circular section, you may have rectangular, square, triangle, whatever. Okay. Under the same torsional moment effect, you are going to get different stress and strain distribution on the section in these different shapes. So, okay, there are many section types, geometrical section types, that's okay. But in this course, we are gonna talk about only circular sections and donuts. Okay. Square hello sections. Let me write. In this course, we will talk about only circular, solid circular section, circular section, circular, and let me and circular hollow sections. Circular hollow sections or donuts. You know. Solid section is a solid section, as you can see, a circle. Circular hollow section is like this. There is a opening at the mid portion of the section. So this is solid, this is hollow. We will only talk about these types of sections. To make the torsion, to make the stress calculation under torsion effect, we make some assumptions at the beginning. Okay, if we don't do these assumptions, we can't solve the problems easily by hand. Okay, at the end of the day, we can solve it, but we have to use complex softwares to solve it. Instead, we make some assumptions at the beginning, and depending on these assumptions, we can calculate all the stress and strains on the section under torsion effect easily. Okay, let's write our assumptions. Okay. Assumptions. Planar sections remain planar. After torsional effect. This is important to make a linear stress distribution on the section. Planar sections remain planar. I guess you're gonna hear about this rule or assumption many times in this course. Düzlem kesitler vurulma etkisinden sonra düzlem kalır. Düzlem kesitler düzlem kalır. Planar sections will remain planar. Why this is important? If we make this assumption, we assume that the stress distribution will be linear on the section. So if it's linear, we can make our calculations easily. We are gonna use similar triangles to calculate the stress wherever we want. So if we don't accept this assumption, the stress distribution will not be linear. So it's not easy to make calculations by hand. Okay. The results change a little bit at the end of the day, but the calculation method will be so complex. Okay, forget about that. We use this assumption and we are gonna do simple calculations for this. The second one. There will be no change on the radius of the section. Or there is no change. No change on the radius of the section under torsion effect. When we apply torsion to our section, okay, there will be a rotation around the axis of the section. That's okay, but we assume that there is no change on the radius of the section. Okay. This is also important. If there is a change, the calculation will be again really complex. Forget about that. This is the simple method. No change on the radius of the section. All the stresses all stresses are in elastic region, in the elastic region. Okay. Remember the elastic region. Let me, if we take a look at a steel stress strain diagram, it was like, there was a linear part here, after that horizontal, like this. The stress distribution under the torsional effects are in this region, elastic region, where the hook rule works, in this region. Okay. And the other interesting and important assumption is the stress, shear stress stresses are zero at the center, at the center of the section. This assumption is important and good to understand how the torsion works on the section. Let me explain this one in the next page. Here, what we said. By the way, the first thing, under the torsional effects, there will be shear stress on the section. Okay. Let me change the wording a little bit. Shear stress occur on the torsion on the sections. Okay. So you need to know what kind of stress are you dealing with. Okay. We are dealing with shear stress in torsion. Shear stress occurs. What was the last assumption? Shear stress is zero at the center point. Let me draw sketch. Here. Again, let's say we have a circular section. Circular. And this is the axis. Okay. And then if we apply the torsional moment on the section, we will see on the section, section is circular, like this. And the stress distribution is this is the center, and here. The shear stress is always parallel to the section. Yes, the circle here is my section, and the arrows, as you can see in red, are parallel to my section. So this is torsional stress. Okay, this is torsion. As you can see, this is center stress. Shear stress at the center is 0, where it gets the maximum value on the perimeter, and it takes the maximum value on the perimeter. So when I go away from the center, I start to get shear stress. There's a good example for this behavior for the buildings in real life. After the earthquake, if there is a torsional problem on a building, you will see the earthquake damage on the perimeter columns. Okay, let me draw a sketch for you here. Let's say I have a building like this. Okay, this is the plan view. So there is a shear wall core here. Let's say this is the shear wall core concrete, and here we have some columns on the right. So under torsional effect, this building, this is the, let's say this portion is the center, rotates like this. So you are gonna see damage on these columns on the perimeter under torsional effects. Yeah. After an earthquake, if you go to damage assessment, if you see this type of damage from outside the building, all the damage, all the columns on the perimeter get some damage, that means there's a torsional problem on this building. So what we know, we always get the maximum stress, shear stress on the perimeter. Okay, on the perimeter, as you can see, on the circular section, left hand side. Okay, how we can calculate these shear stresses? I'm gonna write some equations here. Let me write them. I need a circular section again. A big section. By the way, let me write this equation to the next page. I'd like to complete all the equation in one page. That's better. Yes, here we go. Let's write this circular. Yes, I have this circular section. So um, here is the center point. Okay. This is the radius of the section, and stress distribution on the section. It's like this. The maximum stress is on the perimeter, as you can see here. So let's say we have a small area here. Okay. This orange area, the area of this orange spot is dA. Okay, dA. And the radius for this location is r, small r. And the force on this orange area is dP. Okay. Now, the stress on this orange area is tau prime. The maximum stress here is tau, as you can see. Let's say the stress at this point is tau prime. Let me stress here is tau prime. Now, let's write the equation, the relation in between tau prime and tau. What was the rule? We made an assumption is here, the planar sections remain planar. Okay, this is a good rule to explain this problem. So everything is linear. The stress distribution is linear here. Okay. So if I draw a sketch here like this, this is the center point, and here is the maximum stress location. So the distribution is linear, as you can see. It starts from 0 and goes to maximum, which is tau. That's okay. Where it occurs on the perimeter, where the radius is r. Now, I'm looking for the stress on the orange area. Its radius is r, small r. So I'm looking for this tau prime, and its radius is r. So this is the center, 0 point. So in between these two, tau and tau prime, we can easily write the similar triangle equation. Let me write the equation. Tau prime over tau is r over capital R. So here, basically, we can get tau prime. Tau times r over r. Now, we know the shear stress on the orange area, which is tau prime. This is basic. I guess you understand the logic behind this one. Is there any question regarding this part? How we get the top line. Okay. Now you can see on the sketch there is a dP, which is the shear force, not shear stress, shear force, which acts on the orange area, dP. Okay, let's calculate dP. So at the end of the day, we know the top line, the stress on the orange area, stress times area gives us the force, right? This is stress times area. So let me write here. This is the shear force. Acts on the orange. Orange. EA. Area. Okay. Okay. Now we have the force on the orange area. Now we can calculate the moment around the center. Okay. This is the dm. If we know the force times distance gives us the moment, remember. dP times r, or r times dP, whatever. So this is force, this is distance. This is the moment around the center. Okay. So here, let's make the arrangement on the equation. Let's write here the dP in open form, dm equals r times dP is here, as you can see, top prime times EA. Okay. Now, on this equation, instead of top prime, we can write this equation. Let's write it. R times top prime is tau times small r over capital R times dA. Okay. So we are writing this equation only for this small area. So if we would like to extend this equation to the all section, we are now doing it for a small area. At the end of the day, we are looking for the shear stress on the total area. Instead, we are gonna use integral. So from the equilibrium equation, we're gonna write m torsion. So which is integral of dm. So we put an integral here equals integral saying 2 times r square. We have double r here, one here, as you can see, r square over r dA. Okay. So we can take out of the integral the constant numbers. Let's do it. Equals 2 over r square dA. Okay. So here, what we have, a special part we have. This is almost similar to moment of inertia. Remember the moment of inertia, area times what we were doing in the moment of inertia subject, area times distance square, okay, which gives us the moment of inertia. Here what we have, area times the radius square. Radius is a kind of distance to the center. So this portion is a kind of moment of inertia, but what kind of? Let's write the equation here. So here is I0. This is the polar moment of inertia. Polar moment of inertia. Okay, polar moment of inertia. I'm gonna give you the calculated polar moment of inertia for solid, circular, and circular hollow sections. Okay, the logic is same. Let me write the equations here. I0 for solid. I0 is for hollow. I0 is P times R external minus R internal or over 2. These are the polar moment of inertia equations for circular solid section and circular hollow sections. Okay. We have to know these equations to make our calculations easily. Now, we know what the polar moment of inertia. So if we know the I0, basically, this part is, change color. This portion is I0. So here, equation here, MT. The open form here is, let me write, MT is T over R times I0. So if we are looking for the shear stress under distortional moment, let's take out the shear stress. Is here MT times R over I0. This is the maximum shear stress calculation equation, which is coming from the equilibrium equation given above. So here the unknown is I0 for the solid and hollow sections. You can see the I0 values at the black box at the bottom. You have to know this one, by the way. You have to know this equation. We are going to make examples, but we have to know this one. And you have to know these polar moment of inertia equations. So this is the shear stress calculations under torsional moment effect. Okay, we have one equation for shear stress and two equations for polar moment of inertia. Now, we know how to calculate our shear stress. Now we are gonna calculate the shear strain or strain under torsional effect. Okay, let's do it. I will complete the subjects in the first session, and then in the second session, I'm gonna solve a few examples regarding these torsional effects. And at that time, I guess you are gonna get better understanding about how you can use these equations. Okay. Okay. See. Okay. Calculation of strain under torsion. Vurulma etkisindeki şekil değiştirmelerin hesabı. Actually, the strain under the torsion is a kind of angle. I'm going to explain what they are now. We are going to explain that we are going to calculate that angle as a strain under torsion. Okay. Let's get started. I'm going to draw a sketch for you again. Circular section. Use a line through this. Okay. Oh, the center here is this point. Okay. So it goes like this. And here also the axis comes. What we have on the section, we have torsion here. Okay. Here we have okay, this is R, radius of the section. Okay, this is R. And I have a point here. When we apply a rotation or torsion section, there is a angle change on the section, and also there is one angle change on the longitudinal direction of the member. Now let's write what they are. Here there is a longitudinal angle change. This angle here is gamma, and also this angle on the section is phi. By the way, here this point is B. After rotation, we get this point, B prime. Okay. Now, the length of the member is the length of the member here is L. Okay. So all these angles are so small, really small. We can assume that the tangent of these angles equals the angles itself. Okay, so if you write this equation, gamma here, BV prime, this is over L. So the P over here, P is BB prime over R. So here, what is the relation, the B in between these two angles, BB prime? If you make arrangement on these angles, so the phi, the angle change on the section, L over R times gamma. So here, what we have? We have a shear stress. Let me draw how the shear stress works on a member. Let me write it here instead. So we have a rectangle or square member, let's say. The stress distribution is here, like this. So, so under the shear stress, how it deforms, how this shape deforms, it's gonna get this shape. Take a look here. Okay. Under the shear stress, it's gonna get this red dotted line shape. So the angle here, gamma is here. Okay. Gamma is here. So remember the Hooke's law. Hooke's law. When we were talking about the axial stress, what was it? Let me write it here. There is something similar in these equations. That's why I'm gonna start to explain from Hooke's law. The axial stress equals the modulus of elasticity times axial strain. Okay, axial strain. So here the deformation is, this is the, remember, Hooke's law. Remember our first, one of the assumptions at the beginning, our stresses are in the elastic region. The Hooke's law works in the elastic region. So strain here is, for axial stress, is like this. So this is similar for the shear stress. Almost similar. Let's write the equation. The shear strain equals stress at the top. Here we are talking about shear. That's why the stress is shear stress over at bottom. At the up we have toe. At the bottom we have modulus of elasticity at the axial stress case. Now there is a kind of specific number for shear, which is G. This is what? Shear modulus. Okay, shear modulus. So for the strain equation logic coming from here. Okay. Now we have phi here. We have phi. Let's carry on to write equation. Phi equals L over R times gamma. Instead of the gamma, let's write this part to here. Tau over G. Okay. Phi equals tau times L over G times R. Okay. We know this. And instead of this tau, remember in the first page, we have the tau equation here. Let's put this tau in the equation. So phi equals Or let me write the tau first. Maybe we cannot remember what it is. Tau here is mt over I0 times R. So here, phi equals m tau times L G times I0. Now, this is other important equation. Okay, we have to know. We are going to see how we can use these equations. So I'm trying to explain you where these equations coming from. There is a logic behind all these equations. If you take a look all these calculations, it's not complicated. Okay, we are going to understand how to use this equation. In the next session, I'm going to solve you a few problem. What we said, that's all, I guess. We have two equations today. One for T, which is here, this equation. One for phi, which is the torsional strain. I'm gonna give you, if maybe that's all for the explanation of subject, I'm just gonna give you a table if you work with rectangular sections in your professional life. It's not the subject of this course, but if you need, I just want to give you a table square or rectangular sections. Remember, at the beginning of this course, what we said, we are going to deal with only circular, solid circular, or hollow circular sections. Okay, not for the rectangular sections, but I'm going to give you the table if you need in your professional life. Here, let me draw a rectangle like this. Stress distribution, this is the center. From top to bottom, let's change color. From top to bottom, this is the first part. Here. Yes. Stress distribution here. It's not completely linear. Here we have stress. Elements, as you can see. So from here to here, this is B, and from here to here, this is H, this is B, this is H. So where is the tau max for rectangular section? Tau max is here. Max. To calculate the tau max, we have an equation. You don't have to memorize this one. If you need in your professional life, you can take a look here. There's a coefficient here, which is mu1, mu1. I'm going to give you a table for these numbers. This is the strain, m tau times L, mu2 times G H E cube. Okay. So here the table H over E 1, 1.5, 2, 3, 4, and infinity here. And mu1 number, mu2 coefficient, which are, these are the numbers. If H over B ratio, as you can see, what is H and B ratio, find the ratio from the top of the table, and depending on these numbers, get the coefficients from below. If you have any number in between two numbers, you can make extrapolation. But here, if the ratio of H over B is 1, this means section is square. Okay. If you need these calculations in your professional life, yes, you can use these equations. I think that's all for the first session. Let's have a break, half an hour. It's 10 almost. We're gonna be here at 40. Okay. Okay. See you guys. Okay. I'm gonna share my screen again. Okay, we've just completed all the subject. We're gonna solve a few examples about this subject. So there are some tricks on these examples. We're gonna do it together. Okay. Examples. First example is here we have a cantilever member. At this point, we have two torsional moments. One is 7 ton meter. Other one is 3 ton meter. Okay. And the section here. Section is solid section. Okay, here we have a cantilever beam. On this beam, we have two different torsional moments. One is 7 ton meter, other one is at the end of the cantilever, which is 3 ton meter. And the section of this cantilever beam is solid circular section. The allowable shear stress is 900 kilogram per centimeter square. So if the section carry all these torsional moments safely, what is the diameter of the circular section? Okay, circular section. So here we have to draw torsional moment diagram. You know how to draw the internal force diagrams, moment, shear force, and axial force diagrams. To solve these problems, we need to see the torsional moment distribution on the section, at which portion we have the maximum moment and at which portion minimum or whatever. We need to see the torsional moment distribution on the beam. There is a method to do that. Let me draw the beam here again. So here we have the fixed support. This is the first point. This is the second point. Okay. Now what we are gonna do? How we draw the torsional moment diagram? Okay, please take a look at the screen. We are gonna use the right hand rule. Our 4 fingers will follow the torsional moment direction. Okay, let's have a look to firstly 7 ton meter moment. 4 finger follows the moment direction, and our thumb shows the vector direction. Okay, for 7 ton meter, if we use the right hand rule, we have to use our right hand, not left. Right hand rule. 4 fingers shows the moment direction, and thumb shows the moment vector direction. We are gonna draw firstly moment vectors. Yes, the 7 ton meter goes to right. Good. Let me draw the moment vector here. Okay, this is the arrow which goes right. Okay, let's have a look to 3 ton meter. 4 fingers follow the moment direction, as you can see here. So our thumb shows the moment vector, which goes left. This is 7, this is 3. After we convert these moments to the vectors, the other steps are same as like axial force diagram. Now you can draw axial force diagram for these two vectors. Assume these vectors are like the axial forces and draw the axial force diagram. That's it. That gives us the torsional moment diagram. Okay. Here, if we draw the axial force diagram for these forces, what we get? So we can cut the system from here, basically, and put the positive direction. And we are going to, by the way, the point is here and here. And we are going to see the here axial force is negative, -3. So let's add this part, -3. And after this portion, we can cut the system from here. 3 goes left, 7 goes right. So if you make the calculation here, you're gonna see when you cut this point, the axial force is here, 4, positive 4. Positive 4, so the diagram is like, yes, this is the torsional moment diagram. If you don't draw this diagram, you make your calculations wrong. What you would do if you don't do this, you can take into account 7-ton meter directly, but actually we don't have 7-ton meter on the system. Okay, locally we have 7-ton meter torsional moment, but the distribution, in the distribution or on the diagram, we have maximum 4-ton meter. So we have to consider the 4-ton meter. Okay, what was our equation regarding the shear stress? This T over I0 times R. Okay. Now we are looking for what? We are looking for the diameter of this section. Where is the diameter in this equation? Where is the diameter? The radius is here, and also there is a radius in this equation. So let me write the equation again with the numbers. So this stress, by the way, should be less than tau allowable. Okay. The torsional moment, maximum torsional moment, 4-ton meter. 4-ton meter. Let's convert it kilogram centimeter. I0, what was the equation? P times radius power 4 over 2 times radius. This is the stress equation. This can be maximum allowable stress. This can equal maximum allowable stress. Let's write here the allowable stress and calculate R. So this goes, and this is 3. So there is only one unknown, which is R. P is P, coming from the calculator. There is only one unknown. If you solve this equation, the R cube equals so from here R 6.56 centimeter, but here the question is not R. The question is diameter. 2 times R, E equals 2 times R is 13.13 centimeter. But in real life, we don't use this type of 13.13 centimeter. Instead, round up this number. Let's use diameter equals 14 centimeter. Okay. Okay, you can round up this number. Now, this is the first example. What we learned here, how we convert the moments to the moment vectors. To draw the torsional moment diagram, we have to convert them to vectors. After we convert it, assume it's like an axial force system. Draw the axial force diagram. It gives us the torsional moment diagram actually. Okay, we use the right hand rule here. Okay, let's do another example. See what we have. Yes. So the second example, we have a beam like this. Here is 7 meters. And at the end of this cantilever, I have a torsional moment. Like 3 ton meter. Okay, the section here is have a circular section. Okay, we have a circular section, circular hollow section actually, as you can see. Here this is the center. Here is the R external is 7 centimeter. Okay, 7 centimeter. Question here is actually R internal. So actually, we are asking about the thickness of this hollow section. What is T? Okay. And what is the strain under torsional moment? By the way, what we have here, we have toe allowable. Solve this, which is 800 kilogram centimeter square G. Yes. Under this torsional moment, what is the thickness of the hollow section, circular hollow section? So that means what is the R internal? If we can calculate the R internal, we can calculate the thickness. So this is the torsional moment. Let's draw the beam again here. Let's convert this moment to moment vector. We are going to use the right hand rule. As you can see, the 4 fingers shows the direction of the rotation moment, and our thumb shows the vector direction. That's okay. It goes like this. Okay. Moment goes like this. Okay, which is 3. So if we draw the axial force diagram, what we will see, so if this is the axial force, cut the system somewhere else here. It's gonna be, if you do this calculation, you will see it's gonna be positive 3. Ton-meter. So what we have? We have 3 ton-meter torsional moments on our system. So let's find the thickness of the hollow section. How we can do that? Remember, tau is torsional moment over I0 times R. R here, the total R, external R. Let's write the numbers here. What is the maximum torsional moment on the section? Everywhere we have 3 ton-meter. 3 ton-meter. As you can see, yes, this is 3 ton-meter, and all given information, for example, allowable stress and the G. G is the shear modulus. Remember what it is. They're in all kilograms centimeter. That's why we have to convert ton-meter to kilogram centimeter. Let's do it here. 3 times 10 power 5 is kilogram centimeter. And then here we have radius 7 centimeter. I0. Let's do it. P times external radius 7 power 4 minus R internal 4 over 2. So this equals allowable stress, because we can't carry a stress higher than the allowable stress. Okay. If we are designing a section, if we are calculating the size of a section, we always use the allowable stress. We write the equation, and that equals to allowable stress. Here, allowable stress is 800. Okay. So what we have, if you make the arrangement here, we have only one unknown. Okay, only one unknown. R, I, or by the way, 3 times 10, 5 times 7 times 2 over P. And this and goes like this. Okay. By the way, here you can see the fourth root of this equation we have to calculate. We are going to use the calculators. Please take a look to your calculators and find out how to do this calculation. Okay. Just find out how to do this. It's easy. If instead of this one, you can write a number or a power of 1 over 4. This gives you this number. Okay. You can use this method in your calculators. Okay. Okay, if you calculate this Ri, which is, let me see, yes, 5.20 centimeter. Okay, we have Ri, internal radius. That's okay. What is the thickness of the hollow section? It's easy. The differences between our external and our internal gives us a thickness. T is 7 minus 520 is 1.80 centimeter. Okay. And now the other question, what we did, by the way, we solved this one, this one. The next one is under this torsional effect. If we use the calculated thickness, what is the strain? Calculate the strain. Yes, of course we can do that. Phi is mt times L over G times I0. Okay, G times I0 equals mt. What is mt? Mt is 3 ton meter, so converted kilogram centimeter, 5 times. What's the length of the cantilever beam? 7 meter. 7 meter is 700 centimeter. Okay. Over G. What is G? G is given in the question. Take directly what it is. This is the G. And the next one is I0. What is I0? I0, remember, here I0 is P over 2, the external diameter minus internal diameter. Okay. P times external minus internal, the fourth power of these numbers, over 2. If you do it, okay, now put it here. So make this calculation. Here, the result is 0.0. This is an angle. What is the unit of this angle? It's radians. Okay. The result coming from this equation is radians. Now we complete the question. Okay, is there any question so far? Nope. So another question. If this is okay, so the next one. Here we have a beam again, like this. The total length of this number is 1 meter, and here is A, here is B. At this point, we have a torsional moment and torsion, and the section here is hollow square section, hollow circular section, sorry. Okay, this is the section. The total diameter is 10 centimeter. The thickness here is thickness 1 centimeter, 1 centimeter. The internal diameter is 8. Okay, and toe allowable for this question is 900. The A here is calculate the maximum MT. Okay. And if the torsional rotation angle under maximum MT is radians, calculate the shear modulus of the material. the beam is made of. Okay. So here we have two questions. We need to understand the questions is important here. We have a hollow circular section and we have the allowable stress under this given data. What is the maximum torsional moment? Okay, the first question is this. So the second question depends on the first one. If you solve this wrong, you can't solve the B. That's why you have to solve this basic part correct. You have to be careful. So in the second part, under this maximum moment, if the rotation angle is blah blah 0.0225 radians, calculate the shear modulus of the material the beam is made of. The shear modulus here is, remember, G. G is not given in the question here. We have to calculate the G depending on the given information. Okay. We are going to do the same things. So we have totally two equations. We are going to use always these equations, but we need to understand what we should do, how we should use these equations. Let's do the first one, A. Okay, A. The tau allowable MT over I0 times R. This is the general equation. If we put allowable stress here, it is equals allowable stress, which is allowable. You can calculate the maximum torsional moment. MT is here. So allowable times I0 over R. Now, we have allowable stress and we have R. We need to calculate the I0. I0. Okay. Let's do it. By the way, yes, we can calculate it. Here, P over 2. Now, what is R external? R external is not 10. Be careful. 10 is the diameter. We are using radius here in this equation. Don't forget this one. In the previous years, what I see in the questions, most of our students make this wrong. They directly take the diameter to this equation. No, radius. We are using the radius in these equations. So radius is here 5 over 4 minus. What is the internal radius? The internal diameter is 8 here, 8. So half of it is the internal radius, 4 over 4. Okay. This gives us I0. If you make this calculation, you are going to see this is the this one. We have I0 now. Let's write these in the equation above, MT equation. MT here, the allowable, 900. I0 is this. R is here 5. Okay, 5. So if we do this equation, the result is, let me see, okay, it's like this. Okay, 104,330 kilogram centimeter. Okay. Now we have MT. Under this MT, we have a rotation angle. Let me write the equation again. And T times L, G times L0. Now, what is the question? We know this one, this one, this. This is the question. We are looking for this G of the material. It's easy. We're gonna write all these numbers here, the equation. What was the angle? Angle is 0.025. MT. This one. The length of the member, 1 meter, it's 100 centimeters over here. And G is which is looking for I0 is where? It's here at the top. Okay. So if you make this calculation, you're gonna get a G of 800,000. So here, B starts from here. This is the result of A. This is the result of question B. Okay. See another. Okay. I guess that's all for today. But before that, I'd like to explain one more concept, and then I'm going to close the session. For example, let's say I have a beam like this. As you can see, there is a section change. Here we have, at the beginning, we have a larger section, then we are a skinny section, right? So what we are gonna do, we are gonna, if we like to calculate the rotation angle of this system under any kind of moment, torsional moment, whatever. What we are gonna do, firstly, we will draw the, by the way, the lengths are here, for example, L1, L2. We are gonna draw the, let me write firstly. Draw the MT diagram. Right. Let's say diagram is like this. I don't know. This is an example. Okay, I don't know because I didn't give any diameter here. Draw the diagram and consider each portion. For example, here, consider this portion first with this moment. Write this is phi1. Calculate the phi1 plus this portion, this section. This portion with the length of this portion and the moment. Consider this portion, calculate the phi2. The total rotational angle is, as you can see here, phi equals phi1 plus phi2. Okay, remember the phi, mt times L over G over I0. So for the phi1, consider the moment. For each portion, we have to consider the related moment and its length and related I0. This is constant if the material is constant. So it's generally constant. So we have to find these three unknowns for each portion, then calculate phi1 and phi2 and sum these numbers. That gives us the total rotation. Okay. Now we have just completed the torsional moment, torsion effect on the sections. Next week, we are gonna run a new subject. We have 5 more weeks. 5 more weeks. We will do examples on the, I guess at the last week. We are gonna recap all the subjects because each week we are gonna complete subject with the examples, but the last week we are gonna do applications regarding all the subjects we talked after the midterm exam. I suggest you to join that class. That's all for the torsion. Torsion is important. We are gonna ask about this subject in the exam, final exam. So it's easy. There are only 2 equations. You can use it very well. But to do that, you have to do some examples by yourself. If you Google this subject, you can find many examples. But they might be a little bit difficult for you because it might be for the civil engineers or mechanical engineers. I'm trying to give you the main idea about the torsion. You can try to solve these questions. With these equations, yes, you can solve. And you can find some examples in YouTube. If you search for torsion in YouTube, you can find some examples. You can write torsion for architects and search it. You can get simple examples. That's all for today. Thank you for joining the class. Take care of yourself. See you next week, guys. Okay, bye-bye.